Way back in 1948, a mathematician at Bell Labs named Claude Shannon published a paper that, kind of quietly, laid out the entire mathematical blueprint for our digital world. You see, before Shannon, this idea of information was, well, it was fuzzy, abstract. He was the one who came along and turned it into something real, something we could actually measure, manipulate, and send across the globe.
And wow, the impact was just immediate and profound. This one single paper, a mathematical theory of communication, didn't just tweak existing technology. It literally created the entire field of information theory from scratch. It was so fundamental that some historians say it was even more important than the invention of the transistor, which, crazily enough, happened in the very same year. So how on earth did one paper change everything?
All right, so to really get what Shannon did, you have to picture the world before 1948. Sure, we had telegraphs, we had radio, we had telephones, we could communicate over huge distances, but there was no fundamental theory behind it all. It was like engineers were building these amazing bridges without really knowing the laws of physics.
You see, before Shannon, the word information was all tangled up with its human meaning. It was about what a message said. Now, pioneers at Bell Labs had made some progress, trying to quantify things like telegraph speed, but their work was very specific to the task at hand. What was missing was a universal theory, a set of rules that applied to everything, from a simple telegraph click to a full-blown television broadcast.
And this is where Shannon pulled off his first great act of intellectual alchemy. He put forward this really radical idea. To analyze communication, we have to completely separate the information from its meaning. He made information something you could literally count.
So check this out, because it gets right to the heart of Shannon's big insight. He said that information isn't about its content, it's a measure of surprise, or really the reduction of uncertainty. A message telling you the sun will rise tomorrow, well, that contains almost no new information, right? You already expected that. But a message saying a meteor will strike tomorrow, whoa, that contains a ton of information precisely because it's so incredibly unpredictable.
And to measure all this surprise, he formally introduced a unit that his colleague John Tukey had tossed around, the bit. A single bit is the most basic piece of information you can possibly have. Think of it as a yes or no question, a coin flip. It's the answer that cuts your uncertainty exactly in half. Every single piece of digital data you interact with today is built from this simple, powerful idea.
Now, the crucial thing here is that Shannon didn't just have this cool concept. He backed it up with some serious math. This is his formula for something he called entropy. Now, don't worry, you don't need to calculate it. Just seeing it shows you that this new idea of information as uncertainty wasn't just some clever metaphor. It was a precise, calculable number that told you the average amount of surprise a source could produce.
And that name, entropy, totally intentional. Shannon realized that the math looked identical to the formula for entropy in thermodynamics. As the story goes, the legendary mathematician John von Neumann gave him this advice, partly because it fit, and partly because, well, as you can see from the quote, it gave him a bit of an edge in any argument.
Okay, so Shannon taught us how to measure information. That's huge. But what he did next, you could argue it was even more important. He set out to define the absolute physical limits of sending that information from point A to point B.
Take a look at this. This is the actual diagram from Shannon's paper. It breaks down any communication system, any of them, into these basic parts. But look closely. He includes one element that you can never, ever get rid of: noise. Shannon's theory was the first to treat noise not just as an annoyance, but as a fundamental mathematical part of the whole system.
So back then, the thinking was pretty simple. If you have noise, you just shout louder, right? You just increase your signal power. But Shannon proved something absolutely astonishing. He proved that every single channel, no matter how noisy it is, has a maximum speed limit, a channel capacity. This is the ultimate unbreakable data rate for that channel, period.
And here it is. This is the beautiful formula that defines that speed limit. It's the Shannon-Hartley theorem. And what it says is that the channel capacity, C, really depends on just two things: the bandwidth of the channel, B, you can think of that like the width of a pipe, and the signal-to-noise ratio, S over N, which is just how loud your signal is compared to all the background chatter.
So this theorem was like the ultimate good news / bad news for engineers. The bad news? There is a hard physical limit. You can never, ever go faster than C. But the good news was absolutely revolutionary. Shannon proved that as long as you're transmitting data below that limit, you can achieve essentially perfect, error-free communication. It doesn't matter how much noise there is. You just need a clever enough error correction code. Now, you might be thinking this is all just, abstract theory, but it's not. His core ideas are the direct ancestors of the technology we all rely on every single day. Let's start with something simple, a zip file. It is a perfect, real-world application of Shannon's source coding theorem. The whole goal is to strip out all the redundancy and get the file size as close as possible to its true entropy. The deflate algorithm does this in two main steps. First, it finds repeating patterns. Then, it assigns shorter digital codes to the symbols that pop up most often. It's a direct engineering assault on redundancy, just like Shannon described.
Or how about this, streaming a movie on Netflix? That's all about something called rate distortion theory, which Shannon also worked on. You see, you can't possibly transmit every single pixel perfectly, so you have to make a smart trade-offs between the data rate, the bits you're using, and the video quality. Modern codecs like HEVC are just masterpieces of compression, using all sorts of tricks to remove redundant information and let us stream 4K video over a regular internet connection.
And 5G? 5G is basically a full-on engineering assault on the Shannon-Hartley theorem. How do you increase C, the capacity? Well, you can increase the bandwidth, B, by using those higher millimeter wave frequencies. Or you can improve the signal-to-noise ratio, S/N, by using these massive antenna arrays and beamforming to focus all that energy directly at your phone. Every single part of 5G is about squeezing every last bit out of the channel capacity that Shannon defined all those years ago.
So when you step back and look at the big picture, what's the real legacy here? Shannon's paper didn't just kickstart a new field of research, it gave us a permanent, timeless blueprint for how we think about information itself.
The history of this whole field is pretty wild. After this huge explosion of interest, information theory actually got kind of quiet for a while. The theory was just so far ahead of what the hardware could actually do. But then, with the rise of computers and the need to communicate with spacecraft in deep space, where every single bit is precious, the field came roaring back. And it kicked off this multi-decade quest to build systems that could finally reach those limits that Shannon had proven were possible. And in that way, Shannon's limit became this kind of self-fulfilling prophecy. It's a bit like Moore's Law, which gave chip designers a target to hit every couple of years. Shannon's theorem gave communications engineers a clear, concrete goal: get as close to that channel capacity as humanly possible. It defined the finish line and dared them to get there.
And that right there is the ultimate takeaway. Shannon's real contribution wasn't an invention. Like a better radio or new gadget, it was a discovery. It was like he peeled back the layers of reality and showed us the fundamental mathematical laws that govern how information works. He gave us the very language and the ultimate limits for the age we all live in now. He was truly the architect of it all.